Okay, let's do it. Hey everybody, back again with 5114. I don't know how technical I'm going to get today, but there's just a lot of nuanced technicality here. I want to start just by motivating a question. X bar is the best estimate, or well, a claim anyway. So xi is coming from a normal distribution. We'll make it real simple. You get n observations, IID observations, and I make this statement, x bar is the best estimator for estimating mu. And that's a very loaded statement. And so I think I could defend this. I could also say it's false. So let me just, as a mathematician, say this is not true. So on its own, this is false. I'll write down a caveat. X bar is pretty good. So we use X bar all the time, but this is a very loaded thing. If you were really up on this problem, you'd probably ask me, what's the dimensionality of the whole problem? Probably with me writing sigma squared like that, I'm indicating that it's scalar. You know, if we can imagine this was a vector and this was a matrix, and this is a vector, multivariate normal, answers start changing quite a lot in this claim. And I'm not even sure you could even say this at all in 3 dimensions or higher. Turns out 3D is a breaking point for everything. But we could maybe say it's best in certain, with certain criteria in mind. And so I might say this. So here's the claim. X bar is best, I'll say the best, unbiased estimator. Okay, that's starting to sound pretty good, maybe, but we have to, of course, say what best means right here. And so best might be meaning minimal variance. And if you didn't suppose anything, this would be true. So I'd say this is true. And so let me just write a caveat to all of this. The dimension of the problem is 2 or less for this to even, really be true. So the dimensionality matters. Now, don't worry if you're like, that's not obvious to me. That's not obvious to a lot of statisticians, I bet. We're going to come back around to this. But the dimensionality of this problem does matter for answering it. So this is a minimal variance thing. How do we know this? We've shown this calculation. So Kramer-Rao shows us this. So Kramer-Rao told us this. So let me just write down X bar meets, or I'll say attains, the Kramer-Rao lower bound. And you can explicitly show that. So in that sense, it's best. We're also, when we talk about the variance, we're presupposing the squared error loss function in all of this. And so you've presupposed L2. So this is the L2 condition. It's been presupposed. And if I change the loss function, you might think that you get different estimators. I will say that this can be the best estimator for a lot of different loss functions it can come up. And so this is a special example. But as we know, under L2, so I'll just say the expectation, so the risk function, of the squared error loss of whatever my estimator is, and I'm trying to estimate mu, right here. So this is just our risk function that we saw before. So this is risk. Or if you'd like to, you can call it expected loss. So I think that's totally fine. So what is this thing right here? This is going to be, I'll just write it down in terms of the integral, EX minus mu squared fx given mu dx. I didn't write down my sigma squared because I'm just using it as a constant. So that's what that is. And I can try and minimize this thing. And what we saw last time is this is equivalent to the bias of EX squared plus the variance of EX. So you can just expand that and see that. You can either add in x bar, the expected value of EX, add and subtract and show that. You can even do it directly if you just expand everything, keeping track of all your terms. And I made this claim last time that x bar minimizes both of these. That's very powerful. It's false. It's not actually true. And so you can definitely bring these down. And let me show you how to do it. So let's just imagine true theta was equal to this value. So I'm just going to call this the truth. Usually I call it theta, but I'm just going to indicate this as a specific value. And maybe I know it. So just a specific value. AKA, let's say theta star is equal to 7. Okay, so I just know what it is. And if you told me that, I wouldn't even look at any data. So if I knew this, I would write down theta hat, and this is my estimator. This is theta star. 7. That's a really good estimator. So notice that I didn't use any data to come up with this, but I want you to just look at this. What's the bias of everything? Well, in this special case, and this is kind of a point-wise statement. So I'll make this clear for the mathematicians in here. This has been evaluated. At point theta star. So this is a point-wise evaluation of my method. This is going to be very important. And so at this point, my bias is 0 because I'm right, and lo and behold, the variance is also 0 because it's non-stochastic. And so that's a great thing. And you could never beat me doing anything. It turns out it's not even the case that I need L2 loss in this. You're not going to beat me under any loss function if I gave the truth. And so this estimator is perfect. Now I want to just point out that when you meet the Kramer-Rao lower bound, when you attain it, we call our estimators efficient. So estimators that attain Kramer-Rao lower bound are efficient. So that's a new word for us. Okay, so if anybody ever asks, is your estimator efficient? You would need to clarify with what level of bias are we talking about? So are you saying unbiased? What did you just say? Because Kramer-Rao presupposes it. That calculation goes into the numerator. If you've been reading, putting some bias into some problems can be a good thing. We'll talk about some examples in a moment. If you met your Kramer-Rao lower bound with a certain level of bias that's already pre-specified, we say that your estimator is efficient. This estimator right here, because it does so well at theta star, is called super efficient. So this is a super efficient estimator. Now, I don't want to go into all the mathematical technicalities. This is a real thing. This almost seems like my sense of humor that I would call it something good. This is spectacular. But this is the only place in mathematics where I know when you append the word super, it's actually a bad thing. And so this is super efficient because it does so well there. But there's a trade-off to doing this. So this turns out to be bad. Usually bad. And so there are some expressions out there, I think, that they call estimators that don't do this regular estimators. We're not going to get into it, but if you take an advanced inference class, I suspect you will. What can go bad here is that if you actually generate some data, and that wasn't the truth, and you continue to use that estimator, and so what can happen, albeit the variance will still be 0, the bias is going to increase very, very fast. And so the expected value of this non-stochastic thing minus mu, in our case, whatever that answer is, you know, we're talking about theta, but think about it maybe as mu in a normal distribution. This just looks like a parabola. There's nothing stochastic over here, so there's no expectation. This is just a parabolic function. And so the risk function looks like this. So whatever the thing is, so this is theta star, or guess, but the risk at other values for theta can go infinitely high. This is just a graph over theta. So you'll notice that the risk function is a function of theta. In general, this looks like this. Risk of my estimator and theta is equal to my expected losses. So loss function of theta EX, my estimator, fx given theta dx. So theta is fixed over here. It's also fixed here. It's fixed here. Everything that was stochastic has been integrated out, and so this is a function of an estimator and theta. And so for this particular estimator that we've used, that one, this is what the risk function looks like. No integrations required for that because nothing was stochastic. And so this can become potentially infinity. So this is unbounded. Across theta. And that's easy to see. And so my risk is never bounded. And you can imagine that using something like this, where I say the risk is potentially infinity, that's a concept, you wouldn't like that. And so as statisticians, being conservative people, while we could do really well right here if we were right, on average, we do really poorly. And so because, try to integrate over all of this. I'll sympathize with you if you say I'm not allowed to integrate over it until I apply a prior to that. I agree. So try to integrate this, with any, a flat prior might be common, something like that. Unless that prior is going to sit there and bring down all of the mass on these sides and not allow it, then on average that thing's typically going to blow up. But we don't like that. This is not good. So let me just write, not good. There's too much freedom in this problem to say what's best. Now, I think this is what happens in most of the statistical universe. We have to apply other criterions. And so a lot of times we're talking about we're best, or we can demonstrate that we're good in certain examples, but our examples are a little bit different, and our criterions in which we're measuring things are a little bit different as well. And so this is a very loaded question, what's best? In what sense? What have you constrained? There's too much freedom over here. Here's a couple ways you can think about regularizing or handling the space on theta. And so we can't just evaluate things pointwise at every point. And so somehow we need to deal with the whole space all at once. Because in any pointwise evaluation, it could be great or it could be horrible. And so it's an either or sort of thing. And so I want to talk about my estimators that maybe behave well across the whole space of theta. And how we treat that whole space of theta is which differentiates your decision makers. Here's one thing. So I'll say common ways to deal with the whole space, entire space, where theta lives. Okay, so you need to be thinking about that. And so that's kind of the qualitative insight, I'll say. Treat the whole space of theta and do something with it. Here's one way of doing it. Common. You might say, I want to minimize my risk, but I have to say which risk I feel like minimizing. And so which one? What is it in there? So this is very typical. You might want to minimize your maximal risk. So function of my estimator, no x's in there, and this is a function over theta. And so I'm going to look at my maximal risk on theta. So you're thinking about the risk curve where it's big, and then I want to minimize this on E, the estimator. So I might want to find the estimator that minimizes the maximal risk. So I might call this E hat. That might be best in some sense. This is called the Minimax estimator for obvious reasons. Okay, here's another way you can deal with everything. Instead of just looking at, well, before we get into another way, let me show you a picture. So we can think about this a little bit more. So let's imagine some one-dimensional problem. It's a function of theta. And I've got a bunch of risk functions for various estimators. So let's say I've got a risk function here. Some risk function, and who knows? Maybe it goes down over here. So the risk is really low after I pass an area. Let's say I have some risk function that looks like this. So this might be for estimator 2. And this one might be for estimator 1. So they're functions over theta. And so already staring at these things, there's a perplexing question. Which one of those estimators is better? And you would answer, it depends. I kind of like this because it's kind of constant for a while. That seems good. Maybe it is, maybe it's not. So over in this region of theta, the estimator seems to perform just as well. But over here, it performs really good. But you'll also notice that over in this region right here, this estimator is better. And so already, you can see that when you're confronted with things like this, you don't know which one is better. It depends on what you're going to assume. And so if I integrate it over this range right here, then, well, if I integrate it maybe over this range right here, estimator 2 is better. If I integrate it maybe over this range right here, maybe there's a tie. So again, it depends on what's theta and how do you want to treat theta. Let's imagine that all other risk functions lived up here. So here's the hard part of this is, yeah, I can compare two different estimators to each other, but I don't know about all the infinity of ways that you can estimate something. There's a lot of ways you can do it. Let's imagine all the other risk functions live up here. Live here or above. They're higher risk. So that would be real nice if you had something like that, but there's still a difficult question here, is which one is better? Which one has the minimal maximal risk? I haven't completed my picture, so I'll say that we just stop there. That's where theta lives. And so I can answer that question, that this thing right here, its maximal risk is maybe, I don't know, somewhere around here. So maybe it's here. Somewhere around here. I'll say the maximal risk is that dot right there. This is the max risk for E1 right here. The max risk for E2, well, I didn't finish drawing my picture, so let's just at least draw it. Let's say it goes down maybe a little bit. Give us a little bit of an idea of where the maximum lives. This is the maximal risk. Notice that the maximal risks are occurring in at least my picture, at a point, but there's a whole bunch of other risks that are real close to it. And so this maximization is only happening at a single point there. Obviously, if you had a whole bunch of points where the line was the same, you'd have a little bit of ambiguity as to what you mean. And so how do you pick your estimator in cases like that? But I think if you saw this picture and you like this criterion right here, you'd say, well, even though this risk is low over here, there's a high maximal risk, and I'm not willing to incur that. And so this is a decision you need to make about your decision-making functions. So this is some sort of a decision maker for you. It says use this function for making decisions. But I had to make a decision as to the criterion and how I handled theta in the first place. So think about that for a while. Okay, so I think maybe this is a little bit ambiguous, but maybe it at least leads us to an answer that E1 is maybe best. In what sense? In the minimax sense. So this one is minimax. Of course, we need some theoretical tools to figure out. There's other stuff out there, but it's always above. And in a lot of problems, we don't really know, but I will give you some tricks. And I'll give you some ways that you can be sure about your property, but it doesn't mean that locally somebody else can't beat you. So just keep that in mind. So this is minimax right here. It does not mean that estimator 2 can't be better. Estimator 2 is better over here than estimator 1. yet you're saying, hey, this is the best one. So be careful. Let's look at another, little bit more devious picture. Let's imagine another set of risks. So same graph, theta, risk functions. And let me just draw a perfectly flat. Imagine this is straight risk curve. And I'll tell you about that point in just a moment. So I have risk, so I'll write this as risk E1, theta, that's that thing. And this, imagine I had another estimator that had a risk curve over here. It's also flat. So this is going to be the risk for estimator 2. I'm going to invoke my magic wand, and I'm going to say all other risk functions are up here. This is where we need theory. Start telling us there's nothing else that's better. So I'll develop some of that theory next week. I'm going to ask you some of those questions tomorrow on your upcoming midterm. Don't worry, there's no due date right now. There will be a due date once I decide. It'll probably be about 2 weeks. So just start asking yourself these questions and thinking about them. But imagine this, that this one little point right here lived here. All other risk functions are higher than that, so I don't need to consider them. And I just need to think about these two estimators. And if I were Minimax, right here I look at the maximal risk for estimator 1. It's up there. And the maximal risk for estimator 2 is right here. It's that constant line. This one is smaller than that one. And so the Minimax estimator in this picture right here is E2. So E2 in my picture is Minimax. So you might say, I don't like that. That's not great. And I would argue, depends on how likely you thought that point was. And it depends on what problem we're even talking about in the first place. And so just think about different problems. Risk means different things to you. So I might think about if I were participating in a cattle competition, I want to win, I want the best prediction. I might like, if I end up playing a lot of these games, I might say, well, my utility function is something about my time, I don't really care. So I put loss function of whatever, something minimal on that. And I like to just participate in a lot of different cattle competitions. And I want to win eventually. And so what you might say is I want something that's best on average. So I just want a high probability of being good periodically. And so that's not this situation right here. So if this was something like building a bridge, and I think about, in terms of my parameter space, maybe these are different events that can happen. I might want to guard my bridge against the most extreme thing that can happen. And so saying that, you're still putting probabilities on things happening in the first place. So I don't know if there are situations quite like that. But saying that, if you're building a dam or some sort of structure where people's lives are at risk, you're going to think about this problem differently. You might say, maybe I want to be good on average, or maybe I want to guard against the most extreme thing. Depends on how important things are. But this is a criterion that can be based off of what happens just at one point. So the maximums, presumably, if they happen at one point, then you're just assessing what happens at one point in everything. And so I'm thinking about just this point right here. That's the thing that told me that estimator 1 was not Minimax. So this is a very extreme condition. Saying that, I think it kind of makes sense. It's appealing in some sense, right here. So let me just make a fact. And this proof is a little bit challenging. X bar is Minimax for mu if, this is in our normal example, I know sigma squared, I'm estimating mu given data that I get to see. So x bar is minimax for mu if the dimension is 2 or smaller. Doesn't matter how you got x bar. If you're a Bayesian, if you're a maximum likelihoodist, it has some neat properties. So if this is a two-dimensional quantity or smaller, I can say it's minimax. And in fact, I can say it's unique minimax in those cases. Turns out, when the dimension is 3 or greater, this is not true anymore. I just want you to know this. We're not going to prove that. If you want to have a read on these proofs, 1960s, Larry Brown, you can't do any better than that. He's the one that told us all this. So Stein ended up telling us a whole bunch about these estimators, and he shocked the world with statements like this. And so this is kind of called, this is the Stein paradox. So note, if dimension is 3 or greater, this is false. And that's going to surprise you. So I never would have guessed this. When somebody showed me this for the first time, I thought they were crazy. So I can demonstrate this for you. And maybe I will do that. But basically we need some criterions to talk about how good is this thing in the first place. Is this the right methodology in the first place? And how do we figure out what these estimators are? And can we say that they're unique in general? And people have been spinning their wheels on this problem right here for a very long time. There are no good, just absolute concrete, here's the method for doing it. A lot of times this can be a calculus of variations problem. A lot of difficulty in solving this problem in general. And anybody that works in an optimization field knows this is a hard problem depending on what R is. And even for simple R's, this can be an incredibly difficult problem. Remember, there's a whole collection of estimators that you can plug into this. Theta, you know how to treat it. It's the thing that appears in your likelihood function or your sampling function. You understand its relationship to X. What you don't know is all of these different estimators. Now, one thing we can do, and this is what a lot of people will do, is they'll take their techniques, MOMs, Bayes, MLEs, and they'll come up with a collection of estimators, and then they'll compare which one is best of that collection. No guarantee that there isn't something out there that can beat you. And I would say a lot of applied statistics is just like that. And that's okay. Of course, if somebody's got a theoretically better estimator and it's proved somewhere and you're using this clunky one, you don't look like you know what's going on. So be careful. There's another way that you can treat theta. So I am making this abrupt jump from this problem right here. And I'm going to start talking about kind of a Bayesian way of dealing with everything. But let me tell you where we're going with this. Let me tell you one more example. This one's really simple. It does appear in your book, and I'm going to ask you about it on the midterm. So basically, I want you to read through this example very carefully in your book. A lot of people use this example. If you Google search on it, you'll find this example everywhere. Everybody's liked this example for quite a number of years. Xi's come from a binomial distribution. So this is the number of successes. I'll just say X, okay? One data point, but I'll comprise this of n Bernoullis. So I'm kind of flipping the coin n times, so one data point's good enough for me. So and that's true key right there. So I just have this number of successes. So plenty of asymptotics here, if n were big, even though it's real lightweight construction. You'll recognize this is the minimal sufficient statistic from a Bernoulli distribution. So I did flip the coin n times, and I looked at all the ones and zeros. It's IID, it's all exchangeable. The order doesn't matter in the first place, and all I care about is the number of successes. That's what a binomial gives you. So here's a fact. X over n. So this is your MLE. Oftentimes it's a MOM estimator. And under some conditions, turns out under Haldane's prior, this is the Bayes estimator. Let me help you with that last bit. I say Bayes, you ask which prior, why? So this is under the prior beta, 0, 0. Not a uniform. You'll notice that the map estimator is the same as that one. Or sorry, not the map. But this isn't putting any penalty in everything. So when I look at the expectation, I guess I need to tell you one other thing in here, is I need to tell you which loss function. And this is under L2 loss. So that's the full specification. I need to tell you loss function. I need to tell you my prior that I'm working with. But this is under a beta 0, 0. This thing right here is not optimal. And I need to tell you the criterion under this loss function in this sense. So it's not minimax. So fact, this is not minimax. I'll say minimax. So you can put an A here, you can put a dash here if you wanted. So that might be astonishing to you. And so there is a question of how do you find a minimax estimator in all of this? And I would not use this explicit framework to do it. And so the exercise that you'll see in the book will walk you through a Bayesian procedure for coming up with the answer to this. There's a lot of theory that compounds in that example, so please read through it and we'll be discussing it. But here's what a Bayesian does. Let me write the last bit. Question, can you find, and we might say the unique, and this is a very hard thing to do in general. Unique, let me get you some darker pen. Can you find the unique Minimax estimator for P? And it turns out, yes, you will be able to do it. Yes, and it exists. And how we're going to do it is we're going to do it via Bayes. So there's nothing Bayesian about the setup of this. I think a lot of Bayesians have become Bayesians because they want to answer questions like this and understand their properties and have a little bit more flexibility than just doing this. I know one Bayesian in particular, that's Jim Berger, that he says this is the thing that steered him. What steered me? I don't know. I like likelihood functions. So I like MCMC. That's really what steered me. I was good at that stuff. So we all have our reasons for our conversions, tools we like. But I can really respect like a decision theoretic reason for doing that. And so while we can't always answer this question right here, Bayes is an operating procedure for at least giving you good qualities out of your estimator. It might not be the best thing, sometimes it is, and sometimes you can prove that it's minimax, and I'll tell you all kinds of different ways of doing that. So again, these aren't guaranteed to be unique in general. In some very specific problems, it is. So it turns out this is the unique minimax estimator for mu if the dimension is 2 or smaller. My big caveat is if we move dimensionality up to 3, that's not true anymore. We can come up with a lot of good estimators. Okay, so here's what a Bayesian does. So this is our other decision-making criterion. It's very common. And there's other ones, you can imagine them. So you can deal with entropy functions if you wanted to, and people have tried out a lot of different things, and it seems that these two are the standards that linger around and people play with regularly. Still lots of research to be done here. But I like this setup because it's actually an operating procedure. And so I could end up coming up with E hat Bayes. This is a Bayes estimator. This is the technical Bayes estimator that we've been talking about, and the book has been talking about for a while. So, Bayes estimators. And this is going to be my risk function. You'll notice I oftentimes switch the order of those things. It doesn't mean anything special to me. It's just an argument of both things. Just be consistent in your papers or whatever. I apologize for always shuffling it. And so I might want to minimize something. We like that. So I want to minimize over E, like minimizing the risk, finding the estimator that minimizes something, but I'm going to treat this a little bit differently. Over in the minimax, unmaximized, here's what Bayesians do. They average. That's it. So here's my prior. Now lots of discussions. Which priors, why? But really, this is a weighting function. Weight on how likely theta is pretty poor English. But how much weight do you want to put on different thetas? And so we've got our risk function. So what I might do is I might say, if I knew something about something, or if I had good mathematical justification, I might say, this stuff never happens out here. That's all very nice, doesn't occur. If you're a scientist, maybe you had good rationale for saying that's actually not possible. So we use this function, but we truncate it. And so maybe I think that values over in this region right here are very likely. And I think that these are moderately likely. And I think this stuff doesn't happen. So let me just write that down. Does not happen. Maybe. Probably. So I might build a prior. I might say, well, probably my prior is going to look like this. Maybe. I'll put a little bit of weight there. And this stuff is no, but me being me, I never say 0. I say a little bit of very unlikely weight. Now that was all very subjective, and it depends on the problem, and it depends on what's going to happen depending on if you're wrong over these spaces. You might want to think about that, and that's why answers to these questions are always different. This was pretty arbitrary. Maybe you like smoothness, so you have some decaying function. Who knows? Or maybe you have some very good mathematical rationale for coming up with your prior. And a Bayesian class will teach you more of that rationale. But this is treating theta by averaging over it. And so this is saying, on average, how well is this estimator performing? This is the one that minimizes the on average risk. Do you want to talk about your stuff on average or do you not? You want to talk about the most extreme thing. It depends on the problem at hand, and that's not a mathematical question. So of course, how you solve these problems, that's mathematics. Now let me say a few facts. Facts. Let me just say one fact right now. If the risk of E hat Bayes is constant, so it's flat as a function of theta. So constant over theta. So what I mean by that is I have a risk function right here, flat. So constant over theta, then it is minimax. So solving this problem can give you insight into solving that problem. There's a connection between those two things. And we can prove this. Let me give you a verbal proof real quickly. If something is lowest on average, then it's lower than something somewhere. And there's a relationship between this estimator and that one. So I want you to just think about what it means to average. And so if it's constant and it's on average lower, what does that mean? That means that the maximum is also lowest because it's constant. And so I'll let you think about that. You can encode that into a mathematical proof. But just think about this. So there is a bound on the risk function, this thing right here. Once I integrate and that thing, you know which one is bigger or smaller. What do you think about that? It's got to be this one. And if it's constant, it has to meet that. We can go through that a little bit later. But what I really want to point out is that solving this problem can help us to solve this problem. Turns out, this is called the least favorable minimax estimators. This is really a bad way of doing it. So imagine this. So I'll say, just give you some terminology. It's also called least favorable. Now, just because you're the least favorable thing doesn't also mean that you can't be the most favorable thing if there's only one thing. So in unique settings, this isn't a bad thing. If there's a whole collection of minimax estimators out here, this is your worst one that you could come up with, but you can do it for free. And I'll tell you how to do it once I tell you how to solve this problem. And solving this problem is actually not very difficult. Solving this problem is much more difficult. Let me just show you a picture. Least favorable. Imagine I had a minimax estimator. So I'll just say this is my risk function for different estimators. Let's imagine my maximal risk for my whole collection of estimators happens right there. So we'll let this be the max right here. So maybe I have a risk function that goes through that point right there. So that's the maximal thing. I've got other estimators that are worse. So I've got whole bunch of estimators up here. I know that the maximum, they could come down lower too, no big deal, they're allowed to cross. I know that the maximum risk, so this one is high, that one's higher, this one's lower, right here. I know the maximal risk, if it were minimax, can't be any higher than that point. That's what it means to be minimax. So I'm going to just make a claim, let this be minimax. So risk E minimax in theta. But there could be another one out there. And so the least favorable one, if it were constant, will also be minimax because if you think about how averages work, but the Bayesian one's going to look like that. At least if you come up with a constant one. So if you think about this right here, so this might be the risk of E, I'll call it least favorable. Theta is flat. These are both minimax estimators. If I presuppose all my other risk functions are up there, at least my maximums of my risk functions never drop below that point. This risk function is worse than that one. So they're both okay. You can use them both. And so this one almost beats this one everywhere, but not quite. They tie in a point. So because of this one tie, the terminology is that they're both admissible. And I'll tell you what those terms are soon. Both admissible estimators, you're allowed to use them. Admissibility is a criterion saying that there isn't another estimator out there that exists that is lower in risk everywhere. If there is, you shouldn't be using the estimator you're comparing it to. So this is mostly conceptual right now. It's just things that you need to think about before we go into some math on all of this. There could be ways of coming up with minimax estimators through this format, dropping that constant condition right there, and it could be maybe your most favorable estimator. Of course, this theorem won't do you any good, right here. And so what this really tells me, if I only cared about minimaximality and that was the only thing to care about, then I always have this sort of procedure that I can apply. It's minimax, there must be more to it. It's kind of my take-home point here. Okay, let me show you something. How Bayesian actually operates when they do this. So let me just write down, again, E hat Bayes is equal to the integrated risk. I've got my prior, d theta. I'm just going to rewrite what the risk function looks like here. That's another integral. This is over the loss function. So I've got my estimator with my data plugged into it, theta. And then I'm going to integrate this over my data set. dx, pi theta, d theta. That's just another way of rewriting it. So this interior integral is just the definition of risk. So exact same thing. I'm going to rewrite this just real quickly. I'm going to write it like this. Loss function. Fx. Given theta. Now, I want you to appreciate this integrating bound right here doesn't depend on theta. So I can pull that right through here. You can always do that. But I want to divide by something, and I'm going to multiply by something as well. dx d theta. Okay, and so mx is my margin on x. It's what you might expect it to be. Mx is just equal to this. Integrate the likelihood function over theta given x times my prior d theta. You'll appreciate that this thing right here is your likelihood function if you're operating on theta. So let me just rewrite that. It's the exact same thing. Fx given theta. That's the mathematical function. I play around with theta. I'm thinking about it as a likelihood. So that's my margin. And you'll recognize this thing as the posterior distribution. So another name for this is pi theta given x. That's the posterior. My quick and dirty answer, if I'm feeling contentious, and I don't really want to answer somebody, you're Bayesian if you operate off of this. If you use that function, that's what makes you a Bayesian. So, of course, lots of ways to do this problem. Lots of different ways of calibrating priors. So what kind of Bayesian are you? There's a whole subclass. So now I'm just going to do a little bit of arithmetic. All this stuff is positive in here. So likelihood functions, your sampling function, positive, positive, positive. This thing is positive. It's actually a norm on everything, so it's not exploding. So lots of regularity in this problem. And I'll just mention, this is something we can do when that happens. I can exchange those. You can always do it if the integrals are bounded or conditions on the integrand. And so there's domination theory, all kinds of different criterions that you can look at. And I'll let you take a more sophisticated inference class for all those generalities. This is Fubini's theorem. So I used to call it, like grad school Fubini's was, you can always switch these things. Turns out in one of my Monte Carlo methods that I've come up with, you can't actually switch the order of integration. So it kind of jumped up in one of my own problems that there are times where you can't do this. So I kind of, after a while, started to think, it seems like you can always do it for any practical problem. Not always. Okay. We're not going to dwell on Fubini's too much, but I'm going to integrate, and I'm going to change the order of integration. Oh, and I've made a mistake. Oh, I got it. Just didn't see it. Everything's good here. So what I mean when I interchange those is I'm interchanging these as well. So I'm interchanging the order of integration. So let me just rewrite this. Loss function. Posterior distribution. D theta. I'll do this all in one step. I can pull mx outside of all of this. So it's that one. I've switched the order of integration. I have d theta. This doesn't have any thetas in there because I've integrated them out. And so I have mx over here. dx. Right? You might think I haven't done all that much. But if we're going to minimize this thing, arg min over e, right here. So that's what we're doing with that to induce the Bayes estimator. So I'll just write this part right here as the part that we've just carried over. And so to come up with the Bayes estimator, we need to apply the arg minimizer over E and try to figure out what it is. One nice thing happened is to solve this problem, I don't have to think about this double integration. All I have to think about is the integration where E lives. This doesn't have anything to do with E over here. So there's no E's. And so to optimize this right here, all I have to do is optimize the interior integral. So this is the same as arg min E integral loss function x theta posterior. D theta, right here. So the question is what is this? Most of you would be able to recognize it. So this is the posterior expected loss. It's a conditional statement on the data. So given a data set, it tells you how to operate. I kind of like that. There's also lots of nice properties to doing this. And so let me just say a fact. So a few facts. Under L2 loss, squared error. So this thing would just look like this. EX minus theta squared. Under L2 loss, the best estimator. In what sense? Well, it's presupposing some sort of a prior in here, so keep it in mind, but in this sense, right here, and in the integrated sense, where I'm integrating over all of theta. So the best means something, it means something different from what somebody else might mean. So under L2 loss, the best estimator, presupposing pi theta and Bayes estimation that might seem obvious to you, but what that means is averaging. So averaging over theta is what that means. So best in this sense for L2 loss is the posterior mean. Expectation of theta given x. That's pretty easy to do. And so it turns out, under some classes of priors, I might be able to get back and say, this thing is x bar. Maybe if I consider it a limiting sequence of priors, maybe I say the best thing out there is x bar. Then I look at the risk of all of this. Well, it depends on how I form this. If I used a flat prior, this would come out to be just x bar in that. And it's constant risk, i.e. the risk of x bar. Using that estimator, and I could form this as a Bayesian. It's constant. It's, therefore, given our theorem, if you bought it, minimax. And so totally different thing. Let me show you a little bit of math, just to show you this. Same math that I did last time. If you like squared error stuff, you like means. So that's what I said. Where are you going to build your estimation if you like squared error? You're going to put it somewhere in the middle. In what sense? Well, in the physics sense, where I balance some weighted bar. So that's what a mean is. Okay, so let's just look at this integral. I'll just write down e minus theta squared pi theta given x, d theta. I want to find the best estimator right here. So I'm going to take a derivative with respect to e. You've seen me do this before. I can slide that right over the top. Don't need any special conditions to be able to do that. There's no e's on the boundary of that thing. It's never going to happen. And so this is just going to be the integral. I take my derivative with respect to e. That's 2e minus theta pi theta given x d theta. That's my derivative right here. Derivative with respect to e, again, I interchange the order of those things all the time. There is no negative sign here this time that I've done it. You'll notice that compared to what I did last time, it didn't matter. Because what are we going to do? To find optimal e, I'm going to take this thing and set it equal to 0. So this is no longer an equality when we do it, it's a string of equalities. And I've got to say what I just did. Put my hat right there. I'm using the Bayes procedure, so I might indicate that this is the Bayes prior. So that disappears right here. I wind up with integral of e pi theta given x, e hat d theta is equal to theta pi theta given x d theta. I love it. That doesn't have any thetas in there. If you use thetas as your estimators, it's the biggest mistake you can do in my class because it's not an estimator. So I pull that outside, e hat, Bayes, and I integrate over that. I've normalized everything. That's 1. So e hat is equal to this thing right here. This is the expectation of theta given x. So here is a best answer when I presuppose some conditions. I do like this. I don't usually say doing things that are easy. That's a good reason for liking them. This also has good properties. It's best on average. So Bayesians, if you do this Bayesian thing, you are presupposing you're best on average, and you need to say how you're averaging. What's your weighted averaging procedure? How'd you come up with the prior and why? But in that whole collection of estimators, you can easily determine the best one if you presuppose your loss function, and we presupposed it to be L2. Here's a fact. I think I'll conclude with this. These days, I live for stuff like that because it actually makes me laugh and take my mind off of things. L1 loss. This is absolute. So just my estimator minus theta, absolute value. So that's what I mean. The optimal Bayesian answer or the Bayes estimator is the posterior median. For 0-1 loss, the optimal Bayesian answer is the posterior mode. So you might say, it's not good enough to just be close to the right answer. I want to be able to hit it every once in a while. And so this is, of course, just penalizing you on if you're close, but this is saying you got to hit that thing. And you could tailor that and come up with different answers, but these things from the posterior, they mean different things depending on what your loss function is, and I kind of like that. And of course, there is relationships between all of this back to minimaximality theory. There can be connections. So I want you to see if you can prove those. And I'm going to ask you to maybe do that on your midterm. And basically, I want you to validate to me that you know proofs for this. This one's probably intuitive, but I don't always like saying that because if you just don't see it for a second, that might confuse you. So maybe think about this, see if it's obvious to you. In this one, you're going to have to mathematically prove. I've proved this one for you. That one's easy. You can't do calculus here. And so there's some problems in Casella and Berger, and there's one in particular that will lead you to this. So I want you to work through those problems as well. I like this simply because I don't have this very hard mathematical problem that I need to deal with. I will say something about this, that in my Bayes estimation, if I pick my prior, so this is fx given theta pi theta over mx. If this prior is integrable and it doesn't blow up to infinity, there's one thing you can say about this, and this is always true, and I'll tell you a little bit more about this on Monday. This will always beat something somewhere, guaranteed. And so it'll never just be completely blown out of the water by some other estimation thing. So somewhere in theta space, if I pick my prior not to blow up when I integrate over it, this is guaranteed to be better somewhere. It's on average better, but it's also better guaranteed somewhere. You'll be able to think about that. And so that should be pretty intuitive. If you're lowest on average, you're lower somewhere. So that's because we're adding up all positive numbers in all of this. So if you're averaging stuff is lower than something else, something had to be lower in the first place. So that almost sounds like a mathematical proof, and I bet you could do that yourself. And so this is guaranteed to be optimal in some sense, and that's what we're arguing about all the time. So midterm coming out, think about days that you would like to get together maybe and do a review session so that we can answer questions about all the midterm stuff. So until next time, you guys.